vision. A lone astronaut glows beneath the silence. Then a faint sound, a tiny scratch. You've probably imagined it, floating in space, weightless, the Earth turning below you like a living marble. No traffic. No noise, no gravity dragging you down, just you and the universe. It looks peaceful, it looks silent, it looks safe. But here's the uncomfortable truth. One scratch on your spacesuit, not a rip, not an explosion, just one small scratch could mean your death. Not in minutes, not in an hour, in seconds. That sounds dramatic, maybe even arrogant. Surely we've engineered something better than that. Surely modern technology can handle a tiny imperfection. Let me ask you something. If you poke a tiny hole in a balloon, does it politely deflate, or does it violently tear itself apart? Why? That why is the entire story. And it's not about engineering, it's about physics. Inside your spacesuit is something incredibly ordinary. Air. Not special air, not magical astronaut air. Just nitrogen, oxygen, a mix of molecules flying around at hundreds of meters per second. At room temperature, the molecules in the air around you are moving at roughly 500 meters per second. That's faster than a rifle bullet. You don't feel it because they're hitting you from every direction at once. Pressure is simply molecules colliding with surfaces. Now here's the key idea. Pressure is imbalance waiting to happen. Inside the suit, high pressure. Outside in space, almost perfect vacuum. The universe does not like imbalance. And physics has a rule about that. It's called the second law of thermodynamics. Entropy increases. In plain English, differences disappear. Hot spreads to cold. High spreads to low. Concentrated spreads to diffuse. Every, single. Time put a drop of ink in water. Have you ever seen the ink spontaneously gather back into a drop? No, not because it's impossible, but because it's unimaginably improbable. The molecules are constantly moving randomly, and there are vastly more spread out arrangements than neatly gathered ones. Order is rare. Disorder is overwhelmingly likely. Now imagine the air in your spacesuit. It's like trillions upon trillions of tiny particles crammed into a small region. Outside, almost nothing. That is an extreme imbalance, and the moment you give those molecules a path outward, even a scratch that becomes a weak point, entropy wins. Violently. Let's go microscopic. A scratch weakens the material. On the atomic scale, it disrupts bonds in the fabric's structure. Polymers that were distributing force evenly now concentrate stress at the tip of the scratch. This is called stress concentration. At the very tip of a crack, forces amplify dramatically, sometimes hundreds of times stronger than the average stress. Why? Because forces in materials are carried by atomic bonds. When you remove bonds in one place, the remaining ones must carry more load. Imagine 100 people holding up a heavy platform. Remove one person. The others barely notice. Remove 10 in one corner. Now that corner strains. Remove enough, and snap. A scratch is not cosmetic. It's a local rebellion against structural equilibrium. You've seen this with a balloon. You poke it with a needle. Pop! But here's the deeper point. The balloon doesn't explode because the hole is big. It explodes because once the material begins to tear, the internal pressure pulls the tear wider. The force isn't external, it's internal. Your spacesuit is a high-tech balloon. Inside, roughly 4.3 pii of pressure in NASA's EMU suits. Outside, nearly zero. That difference doesn't sound like much. But multiply it by the surface area of your body, and you're talking thousands of pounds of outward force trying to escape. Your suit is under constant tension. It's winning a silent war against the vacuum every second you're outside. And what is vacuum? Not cold air, not empty darkness. Vacuum is almost nothing, which means the moment a pathway opens, gas doesn't leak. It accelerates. Remember those molecules moving at 500 meters per second? They don't need to be sucked out. They are already moving in all directions. If one direction leads to emptiness, statistically, trillions will take it instantly. The pressure equalizes at the speed of chaos. On the micro level, molecules randomly collide. Some find the hole. They escape. Pressure inside drops, but escaping molecules create local turbulence. The material flexes. The crack widens. More molecules escape. Runaway process. On the macro level, you see a catastrophic tear. Seconds, maybe less. Now let's address the myth. Would you instantly explode? No. Your body wouldn't explode like in Hollywood. That's fantasy. Biology is physics, and physics is more subtle and more terrifying. Your body is mostly water. Water boils at 100 degrees Celsius at normal pressure, but boiling temperature depends on pressure. Lower the pressure enough, and water boils at body temperature. This is called ebullition. In vacuum, the fluids in your mouth, your eyes, even the moisture in your lungs begin to boil. Not because they're hot, because pressure is gone. Boiling isn't about heat. It's about vapor pressure exceeding ambient pressure. Physics again. On the microscopic level, water molecules are constantly jiggling. Some have enough energy to escape into vapor. Normally, atmospheric pressure pushes back. In vacuum, nothing pushes back, so they leave. Your saliva would begin to bubble. Your blood wouldn't instantly boil because it's under internal pressure from your circulatory system, but exposed fluids would. You would lose consciousness in about 10 to 15 seconds, not because of explosion, but because oxygen can't reach your brain. Your blood needs pressure gradients to function. No external pressure means no proper gas exchange in the lungs. Again, entropy. Oxygen molecules diffuse outward. Carbon dioxide balance collapses. Cells starve. Life is a constant fight against diffusion. Let me say that again. Life is a constant fight against diffusion. Your cells maintain concentration gradients. Sodium here, potassium there, like tiny chemical dams. Your lungs maintains oxygen gradients. Your body maintains temperature gradients. Your very existence depends on maintaining differences. And the universe erases differences. Relentlessly. Put an ice cube on a table. It melts. Not because it wants to, but because statistically, there are more ways for molecules to be in liquid form at room temperature. Life is the ice cube. Space is the warm room. Your suit is the refrigerator. Scratch the refrigerator, see what happens. Now you might say, fine, so make the suit stronger. We do. Spacesuits are marvels of engineering. Layered fabrics, micrometeoroid protection, pressure bladders, thermal regulation. But here's the uncomfortable truth. You can never make something perfectly strong, because materials are made of atoms. Atoms have bonds. Bonds have limits, and random impacts happen. Micrometeoroids travel at 10 kilometers per second. At that speed, a paint fleck has the energy of a bullet. Space is not empty. It's a shooting gallery of entropy. On the microscopic level, an incoming particle transfers kinetic energy to atoms in the suit. Bonds break, heat forms, shock waves propagate. Materials aren't continuous. They're lattices of vibrating atoms. Cracks form where vibrations exceed bond strength. There is no such thing as perfect rigidity. Only probability, and here's where it gets profound. The reason one scratch can matter is not because the universe is cruel, it's because the universe is statistical. Let me give you another analogy. Imagine a deck of cards. Shuffle it. You get some random order. What are the odds of that exact order? 1 in 50, 2 factorial. That's a number with 68 digits. Astronomical. Yet you got that order because every order is equally improbable. But here's the trick. There are vastly more messy states than ordered states. Air evenly distributed in space? Messy. Air confined neatly in your suit? Extremely special. You are living inside an improbability bubble, literally. Your suit is a tiny island of low entropy. Earth's atmosphere is a larger island. Life on Earth is an even stranger island. And islands require boundaries. Boundaries require structure. Structure requires energy. And energy flows from hot tea. Oh, cold, from concentrated to diffuse. Always. Where does the energy come from? The sun. The sun floods Earth with low entropy infrared photons back into space. That imbalance allows complexity. Plants grow. Brains think. Civilizations build rockets. But in deep space, far from atmosphere, you are stripped of that buffering system. You are face to face with the raw statistical tendency of matter to spread out. No cushion. No mercy. Just probability playing out. Now let's confront the counter-argument. What if we just repressurize quickly? You can if the leak is small, but if a scratch propagates into a tear, the depressurization timescale can be seconds. Pressure equalization in gases happens incredibly fast because molecular speeds are enormous. At the microscopic scale, everything is already in motion. We live in the illusion of stillness, but stillness is just balanced chaos. Remove the balance. Chaos shows its teeth. Have you ever seen a dam break? At first it's just a crack, then water seeps, then erosion widens the gap, then collapse. The water doesn't decide to destroy the dam. Gravity and pressure gradients simply do what they always do. A spacesuit tear is a dam break in reverse, air rushing outward instead of water downward. And here's something even more unsettling. You are not a closed system. You cannot survive by sealing yourself perfectly forever. You need exchange. Oxygen in, carbon dioxide out. Heat out, energy in. Life is an open system that maintains internal order by exporting entropy. You survive by dumping disorder into the environment. In space, the environment is mercilessly efficient at taking it. Too efficient. Zoom all the way down. Atoms don't know about you. They obey quantum mechanics. Electrons occupy orbitals. Nuclei vibrate, bonds stretch and snap. Fate, macro-level story, astronaut tragically lost, is just trillions of microscopic events obeying Schrödinger's equation and statistical mechanics. There is no villain, only laws. And the laws say, pressure differences disappear. Temperature differences disappear. Concentration differences disappear. Eventually. Always. So why go to space at all? If it's so hostile, if one scratch is fatal, because here's the paradox, the same laws that make space deadly make life possible. Entropy increases, but local decreases are allowed, as long as total entropy increases elsewhere. You are a temporary defiance, a pocket of order carved from chaos by 13.8 billion years of cosmic evolution. Stars forged carbon. Supernovae scattered it. Gravity assembled planets. Chemistry stumbled nervous systems. And now, the universe has built a creature that can step outside its atmosphere and look back. That is outrageous. When an astronaut stands on the moon and looks at Earth, they are seeing a thin blue line. That line is everything. A fragile membrane of gas a few kilometers thick. That's all that separates oceans from vacuum, forests from freezing darkness, breath from suffocation. We evolved under that shield. We forget how miraculous it is. One scratch on a spacesuit reminds us, we are not masters of the universe. We are balanced chemical reactions, carefully maintained pressure gradients, walking thermodynamic miracles. And here's the philosophical pivot. The fragility is not a flaw. It's the price of complexity. If the universe did not relentlessly erase differences, stars wouldn't burn. If stars didn't burn, heavy elements wouldn't form. If heavy elements didn't form, you wouldn't exist. The same entropy that would kill you in space is the reason you're alive to contemplate it. Isn't that strange? The V. Lane and the hero are the same law. So the next time you see an astronaut floating peacefully, remember, inside that suit is a storm of molecules. Outside is near infinite emptiness. Between them is fabric, engineering, and probability. A scratch is not just a scratch. It's a gateway for statistics to reassert themselves. It's the universe whispering, balance will be restored. But here's the final twist. You are already surviving in space. Earth is a spaceship. Its hull is atmosphere. Its life support is ecology. Its energy source is the sun. And we are scratching it, slowly, changing its chemistry, altering its pressure balance, warming its surface. The laws of physics don't negotiate, they respond, always. So maybe the lesson of the spacesuit isn't fear. Maybe it's humility and gratitude. Gratitude that for a brief cosmic moment, atoms have arranged themselves into you, into consciousness, into curiosity, into a being that can ask, what happens if there's a scratch? The universe doesn't care about scratches, but you do, because you are the rare configuration that experiences consequence. That is astonishing. So let me ask you this. If your entire existence depends on maintaining fragile differences, pressure, temperature, chemistry, what does that say about how precious those differences are? And if one tiny scratch can mean the end, what boundaries in your own life are quietly holding back chaos? I'll see you in the comments.